we'll get started with some of the basic statistics. And the first one I'm going to use is a Beavers dataset. So this is also one of the dataset that's included with the build of R. So you don't have to download it. You just have to check it. It's already loaded in your R Studio. So if you check the structure of Beavers 2, so this data basically is it's just a recording or a time series data where some beavers, the beavers are some kind of animals, so they are put in a retreat or like an environment, a controlled environment, and they are measured for their body temperature every 10 minutes, and so they also record whether the beavers are active or not active. So depending on whether they are active or not active, they want to see how much temperature variation, body temperature variation there is in the group of beavers that are active versus non-active. And you could do several other experiments with this, but this is basically time series data, and I wanted to show you if you're dealing with time series data such as EMR data, or no, not EMR, I'm sorry, ECG data, which is like every second you kind of look at the peaks and troughs in your heart rate and um, in your the electrical pulses that your brain is sending, and oxygen levels. So that also is a time series data, which means you get one value every time interval. So here in the Beavers data, we have the day, time. Let's just do it in our studio because it's more interesting over here. So if you check over here, the Beavers data, you have you have the day, which is the 3:07. It's the same day, and they are starting at 9:30 in the morning, and 9:40, 9:50 every 10 minutes. That's the time, and they are recording the temperature for that particular time. So that's 36.6, etc., etc. And the active, the last one is active, which is zeros stands for not active, and one stands for active. So if you want to check the Beavers data set in your help window, it shows that there is this is basically some experimental data recorded in 1994, and every 10 minutes for four female beavers, but the data is like one period and one day, and some animals were used. So anyway, so there are two sets of this, beavers 1 and 2. So we are using the beavers 2, and if you want an explanation for each of these columns, it's all here. It's basically Celsius temperature and active, non-active, if the beavers are sleeping or they're inside their cages or they're outside. That's the way they define activity. So let's go back to our data. So the first thing what you notice here, it's a data frame with 100 observations and 4 variables. And what you have is, and the one thing that you will notice is everything here, all the columns are of numeric data types. So the very first thing that you do after getting any data set is to convert some of these categorical values into factors, because you don't want R to treat everything as numeric. You want to be able to perform differences and analysis between various categories. So in these 4, which is the day, the time, the temperature, and active, what do you think should be a factor or a categorical variable? which one do you think should be a factor? So one way, I think the last time I told you, the one way of checking whether a particular data or whether you want to categorize some variables or not, for that, the one way of checking it is just to see the number of unique variables, unique values in that variable. So here, I think everything else is a continuous variable, but just for this active, yes. So the active column is the one you want to convert into a categorical variable because it has only two values, whether it's active or not active. I mean, so you can define it differently, but just in the experiment, they just named it zeros and ones. So if you want to check the unique values, you just use the unique, and you use the beavers $2 active and check how many values there are. So you see that there is only two values. So you remember you did it in the assignment of calculating the unique values or the range of columns just to see how many unique values there are in each of these columns. So let's convert the active into a factor. So I already have it here. So what we do is, if you remember, to transform the whole data set into factors and into factors for some variables, we use this transform method. You give it the data, and then whatever columns you want to change into factors, you could change that. Either you can replace, I'm actually creating a new variable here because the actual variable doesn't have an E for active. So I'm creating a new variable, factorizing that active and creating a new variable. You can replace the same variable. It doesn't matter really. If all that you want to do is see the differences between these two categories. And I'm making the active a factor, and I'm sticking the labels. So this is a transformed beaver set. So now if you check the structure of this transform beavers, it has to be, so this is not changed, but here is a new variable that we created. It's a factor with two levels, and the level labels are here, no and yes. And it's, so the factors, it's actually going to, when we are trying to print the structure of it, it's going to print it in its own format, but the actual values are over here. But don't it's not going to mess up the order or anything. It's just for our display. It's displaying these values. So we can now see the difference of these categories. So right now we are going to use a histogram just to see the distribution of these two groups, whether the temperature in these two groups, active or non-active, whether they are different or the same. So for having different panels of histograms, you see that the general way of making a histogram is using this hist function that we saw in the previous sessions, right? So we give it the beavers 2, and we give it whatever we want to make a histogram for, which is the temperature, and then you see the temperature. But if there is a package called lattice package, I'm going to load that package right now, and you might not have it, so you'll have to use the install.packages and then use the lattice over here. So just that will install your package, and since I already have it, I'm not going to reinstall my package. So I'm loading that package. So what this package does is it can easily create different panels of histograms. And now what we'll create is we'll create two histograms just to see the distribution of temperature in these two groups, active or inactive. So let's go back to our, so this is what I wanted to show you. It's a formula that you have to use within the lattice package. You have the sign tilde, and you have the left side of it and the right side of it. So the left side of it usually is a y or a y-axis, and the right side of it is what you have on the x-axis. So let me see if I can get a pen. Okay, so it's y tilde x. So usually it's in that form. And whatever you want on the y-axis um, should be the column name of the y, and you whatever you want on the x-axis will be on the right side of this tilde. So when we want for a histogram, right? A histogram, the y-axis is always going to be the frequency or the tally or the count of the number of beavers, or in our case, the number of beavers or the number of temperatures for the beavers falling in one particular category. If you remember, if you recall the histogram that we did for the MPG, we count the number of cars falling in that particular bin of MPG gas mileage. So for here, we are going to, the y-axis is going to be the frequency or the number. So what we have here is nothing on the y-axis, because it has to be understood when we are using a histogram function. The usual plotting function in R is hist, but this is the lattice package. So lattice package has a function called the full name spelled out histogram for creating histograms. And on the left hand side, you don't have anything, it's an empty, versus on the right hand side of this tilde, you have a temperature. You have the temperature of beavers. So when you try to do this on your RStudio, this is the line that I was going to run. So you put the tilde, you put the temperature on the right hand side of the tilde, you give it the data, and you run this. So if you run this, you will get the same histogram that we got before if you by using the hist function, and it's going to be so this package just has a default color of blue, and that's why it's displaying blue. I entered any color here, but this function histogram has a default color of blue. But what uses this histogram? So the only thing we notice from this histogram is that we see sort of two peaks, and the data is not really normalized. And if you recall what normality is, in one of our previous sessions, we looked at the bell curve, and the bell curve represents that a data set or any numbers or any column that we are looking at has a peak and has only one peak, and it somewhat falls into the structure and the shape of a bell curve. But here we see that there are two peaks which might not be normal. So it's not, so normal is not a literal word normal, it's a statistical normality, and this having two peaks is not really statistical normal. So and we wanted to see the distribution with the distribution of these beavers' temperatures based on the activity, right? Whether they are active or not. So you could use this this sign, which is a like a dash that's separating the temperature and the next, and here give what you want to distinguish or the data with, or what panels you want. So when we run this, you get here two panels, and on the left hand side panel and the right hand side panel. So if you remember, it's going to be 0 and 1. So we have 0 for inactive and 1 for active. So here what it did automatically for you when you use this line and active on the right hand side of that temperature is that it's going to divide all the data into the two categories that active has and display it based on an increasing order. So 0 activity will be displayed on the left hand side, and 1 activity, which is active, will be displayed on the right hand side. So now we see two peaks, and each of these looks somewhat normal and a statistical normal. So if you imagine like a smooth curve on these peaks, it's going to resemble a bell curve. So on the left hand side, you have the temperature for inactivity, and you see that it's peaking somewhat between 37.0 to 37.2. There is a higher peak, and on the right hand side for the active group, you see that the peak is moved a little bit further away, and it's peaking around 38 degrees. So that's what we expect, right? Usually when beavers or anybody who's active, the body temperature increases compared to when they are at rest. So we see these two histograms here, and this lattice package using this sort of representation. It's easier to divide those and draw the histograms in just with one line of code. So let's go to our next slide. This is what we saw. Okay, so we see from these plots that the data is somewhat normal. If you imagine a smooth curve around these boxes or the bars, you will see that it might represent a bell curve. But that is still guessing. We won't be able to prove it statistically with some statistical functions that the data is normal. So one such way of testing for normality of data is a quantile plot. So, or a QQ plot as it's called. So this QQ plot, what it does is it takes in two sets of data, and in our beaver's case, we will give it the set of temperatures with inactive and the set of temperatures with the active group. So if you give it two sets of data, what it does is it divides each set of data into quantiles. If you remember, the division of quantiles is going to be into 4 groups depending on what temperatures fall in from 0 to 25% of the data, 25 to 50, 50 to 75, and 75 to 100% of the data. So there are 4 quantiles, and depending on what temperatures fall in those quantiles, this QQ plot is going to say just maybe rank these temperatures in an ordered fashion and plot one group against the other group with the ranks. So it's going to sort, R will sort both the samples of the data that you provide this QQ plot with, and then it's going to plot these sorted values against each other. And so from the plot, it does show, it does give an indication of normality, but the way that you actually check for normality is by using this method called QQ norm, which checks for normality of two groups of two groups. And there is also another way. So against So when you compare two groups, there is always a problem of seeing whether if one of what if not what if both are not normal or both have the same mistaken pattern, then it's actually a problem. Then you don't know. It's the plot might be good, but you don't know if it is, if both the data sets are not normal. So what you do is you have another provision in R where you take a theoretical sample set and you which is normal, and you compare your data set against that to see if your data set resembles that, or a theoretical sample size. So let's look into some of these examples here. So what I'm doing here is this is an easy, so even before we go here, I want to just backtrack a little bit because in the previous classes, we didn't get a chance to talk about how to subset a data frame. So let's just go into little details about it, and then we'll come back to the QQ plot. So how do I plot, say we have this transform.beavers, right? So let's just look at the top few rows of the transform.beavers. You have this, right, which is the day, the time, temperature, active, and it's just labels. This is something that we created. So depending on this, how do we extract the temperatures? You know that the active column has two values, 0 and 1. How do we extract the temperatures? And you know that the transform.beavers is a data frame, right? So it's a data frame. So how do you within the data frame, how do you filter, or how do you find out the rows for for which active is 0 and active is 1? So anybody, can you just type into the chat box? How do you extract the rows with activity is 0? Now this transform.beavers has 100 rows. So how do I extract the rows that has activity 0? And you know that activity is 0 and 1, two values. How do, now I want just the rows for which activity is 0. Yes, subset, you could do that, yes. So you could do this. You could do this and you will extract all the rows where activity is 0. So you could see the dimension of this. It's going to be 38 rows and 5 columns. 5 columns is common for both. So it's going to be 38 rows with no activity, and the rest of the 100 rows is active rows. So you could do that, or I have a very cumbersome way of putting it over here. This is a very lengthy process. We usually don't do this. The reason I put this over here is to show you the utility of the with function, which I'm going to come to in just a minute. So what you could do is you could do this as a participant suggested. You could do this subset, and you will get those rows, or you could, if I just want to extract not all the rows, the temperature column of this, then I could use just look at this piece where I'm doing transform.beavers dollar active is 1, and then and whatever rows I get over here, if you just run this part, right, it's a logical value, it's a true or false. So if I give it within the rows of the data frame, what it's going to do is it's going to pick just the values for which it's true, 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 true. So all these true rows, number of rows will come in here, and for those rows I want the temperature. So that's what I did over here. Okay, so we have a question from Dr. Satya. He asks, could you explain why we need the data to be a normal distribution? So so we have a certain testing for statistical um, differences between two groups. Say if we want to see the difference of means between compare two groups and we want to see their differences, so some of the statistical tests like t-tests, they want the data to be normal. The basic assumption behind a t-test is the data has to follow normality. So what we do generally for, say, maybe gene expression, or any other, like, sequencing data counts, we usually normalize it, meaning we either convert it into a logarithm. So if you take a log of anything and convert it into a logarithmic value, it's good, the data is going to be normal. And or we are going to follow one of those normalization techniques where you divide all the numbers with the least count in that column, or you could follow any of those normalization techniques, and the data is going to be normal after that. So one of the reason is because these statistical tests need the basic assumption behind a t-test, for example, is that the two groups that you're testing is normal. So that's why we need it to be normal. Is your question answered? Okay. Correct. What Dr. Satya says is, what I remember is, because we always have access to a partial sample only, and we don't know the exact population, and we'd like to predict about the population based on the sample that we have. Of course, so whenever we are generalizing it to a population too, basically because your statistical tests would have this underlying assumption of data being normal, whatever sample set that you have also has to be normal for those tests to be accurate. So once if you it's the same problem as not normalizing your data. If you don't normalize your data, your results are going to be wacky. They are not to be trusted. So one such example that I can think of right now is a t-test. So we will cover that today, just to see the differences between t-test and the other test, Wilcox test. Usually what we do is a Wilcox test just to be safe, because normality always, depending on what you're using to test normality, if your data falls on the borderline, then you don't want to take chances. So we always use a Wilcox test which does not have those the underlying assumption of your groups have to be normal. So it does not have that. So you could always use a Wilcox test, but however, you will be sacrificing some of your significance if you're using Wilcox test and your data is not normal. So one of the best ways to normalize your data, make sure that it satisfies the normality stats, and then proceeding to do, a t-test or a Fisher test, depending on what you're doing. Okay, so let's go back to our example here. So this is a very cumbersome way of, retrieving just the temperature for the rows which are active, and I have this long syntax over here and similar syntax for activity being 0. So you could either do this, that should work fine. It's just it leads to a lot more typos, and error checking will kind of be difficult. So you get this over here, this plot where it looks like a straight line in between, which is what we want. And you can replace the x-axis and y-axis. These look too big, so you can replace the labels of it. But there is a much better way of doing this sort of extraction and doing the QQ plot with it. So it's a function called width. So you use width, and your first argument is going to be the data frame name. You give it the data frame name, and the second argument is what you want to do with it. So give the QQ plot, and give it two arguments of the two groups that you want to plot. So here I'm giving temperature, but temperature for the rows where active is 1, and the rows where active is 0. So this way I cut down giving my data frame name multiple times. So in the previous one, I gave it like 4 times. I used the data frame, and there are always many more methods like what Dr. Satya suggested, the subset. But you still, even for the subset, you have to give it like 4 times. So these are easier ways of writing code, much cleaner code. So if there is a typo or an error, you can detect it immediately. So the problem doesn't come when you have like a sequential code which is short, maybe 50 lines or less than that. But when you start writing functions, and you have like functions within functions, and you have to test all this code, then it's much easier, and you will appreciate the code being much cleaner than writing more complicated code. It's not really complicated. It's just if you have longer names for your data frame, then typing these will give you more typo errors. And just tracking, for me, just to track this whole line and what's going on for readability. If you give your code to somebody else and they want to see what's going on, just reading this one line will be a little more difficult than reading this line, which is, it's much simpler, just using the data frame and what you want to do with it. So it's a matter of practice. You will get to it, and you will want to use better ways of writing code as you practice more. So this is one way, and we will get into, so when we run this, it's going to give you the same plot, which will look like a line. So the problem that I told you before for checking normality with this type of QQ plot, this is just a plot just to see how the relationship between these two groups is. But to check the normality for each of these groups, you got to use something called as QQ norm. So QQ norm is a way of checking your sample against some theoretical values. So what you have here on the very first line is doing something like the QQ plot, but it's when you use QQ norm, it's going to take only one data set, and it's going to plot that data set against theoretical values. So this theoretical values, as you know, it's a normally distributed value where, you know, 0 is one value, and then you have two values on either side. So then plot your sample set against these values, and then you check for that straight line. So you use something called as QQ line just to be able to draw a line. And if this is falling, if all your points are falling in a straight line, then you assume your data to be normal. Of course, there are some outliers over here and outliers over here. And similarly, for the group where activity is 1, you see that most of these fall on that straight line. So, and some of them are outliers. So it's theoretically normal sample. So even we saw this even in our bar plots when we did combine this data set and tried to do a bar plot. You see two boxes. So the temperatures for both active and inactive groups may not be normal because each has its own peak. But when you separate these two groups into active and inactive groups, they are, and test for normality, they are normal. So just for formal testing of normality, just to tag it with a p-value, usually statisticians always believe a p-value. Let me see if there is any question. Okay. Normally, statisticians believe a p-value. They always want every comparison, everything to be tagged with a p-value. So just for our test of normality, not just visually looking at, you know, whether it's forming a straight line or not, you with a test like this, you can give it a p-value. So this is called a Shapiro-Wilks test, and this is normally used for testing whether a data set conforms to normality or not. So this is the method that you follow. It's called Shapiro.test, and whatever data set you give it, it's going to test for normality. So the output of this line is this. It's going to give you the data set. W is a measure of that test. So usually, be it this test or, you know, any other test like p-test, Wilcox test, we always look at just the p-value, because each of these measures mean different things for the test, but p-value is actually it shows the strength. So what this says is, just for the test of normality, we want this value to be under 0.05. We want this value to be, yeah, sorry, we want this value to be over 0.05 just for the test of normality. I know it's kind of confusing, but I'll show you the difference. Here, the whole of temperature has, again, when it's not divided into active and inactive groups, the data is not normal. And so we have a very small p-value, which indicates that the data is not normal. But when that's what I have it in words for you here. We usually use 0.05 as the cutoff for most tests in statistics, and so even for this. But so according to this test, the data is not normal because we have a very small p-value. We want the p-value to be over 0.05. So when we actually divide it into those two groups, active versus inactive groups, again, this is another way of dividing it into those groups. So you can apply this method and see based on it's an easier way of looking at and doing that test. So you have looked at the apply family of functions already. We had looked at apply, lapply, sapply, but tapply I haven't told you, but I highly encourage you to explore this on your own. It's just basically going to divide your data with the second argument that you give it and apply whatever function you give it to every one of those groups. So in this case, it's more appropriate to do it because we want the temperature to be divided into two groups based on activity 0 and 1 and apply this test sharpie.test. So what it did is it applied that test to activity 0, which is the inactive group. It applied the test, and here we see that the p-value is below 0.05. Or no, above 0.05. So I always, so excuse me for my language, because usually whenever I refer to a p-value for all the other p-values for tests, we always want the p-value to be small. But just for this test of normality, we want the p-value to be big, meaning for all the other tests, this is a very strong p-value, which means the test is possibly true. But just for the test of normality, we want the p-value to be big, and which is big in the sense above or greater than 0.05. And this is certainly greater than 0.05. So we see that the inactive group is normal, and same for the active group, more than 0.05. So each group in itself, they have a normal distribution. So now, getting into comparisons of these two samples. So our initial goal with the Beaver set was to see if the temperatures between the two groups, or the active and inactive groups, are different. So basically our theory is, we are saying that whenever beavers are active, they get up and start moving, their temperatures will rise than if they are sitting back and resting in their cages. So how do we show that difference? We cannot show that difference. Suppose if there is like a 2-degree difference in the two groups, we cannot say it's significant unless it's proven by a statistical test. So we have two tests here that we generally use to prove the differences between two samples or two sample groups, and which is you might have already known of the t-test, and there is another called as a Wilcox test. So t-test, as I previously told you, t-test assumes that the samples be normally distributed. Whatever samples you're testing in the t-test, its basic underlying assumption for the t-test to work and for the numbers to be rightly explained is that the two groups that you're using for a t-test have to be normally distributed in itself. Which is the case for our beavers. We saw that the two groups, the activity and inactive groups, are normally distributed. So we can use the t-test in this case. So there is another test called Wilcox test. So this Wilcox test, it doesn't have that assumption of being normally distributed. However, you will compromise a little bit of significance in the Wilcox test, which is not really an issue in usual in our daily lives, because we always want to be safe, on the safe side, trying to give as conservative p-values as possible, even though it sacrifices some significance. So in a t-test, you give it, you have this t-statistic. T-statistics, we do not really make much sense out of the value of the statistics. It's usually for, when we were learning stats as kids, you remember at the back of your math book, there were tables such as, a t-table or an F statistic table. So that is generally for that. What it does is, based on that statistic, you can look at the p-value significance, but in R, you don't have to worry about that because it gives you everything. The test gives you all the values that you need, so you don't really have to worry about what this t-test statistic corresponds to. So it gives you the statistic, it gives you the degrees of freedom, Degrees of freedom, I will come to it in a little bit of time. For today's session, you don't have to concentrate on that. The only thing you'll have to focus on is the p-value. So as the smaller p-value in a t-test, the smaller the p-value, the bigger is the difference between the two samples that you're testing. So that is what we want, right? In our Beavers example, we want to be able to show that the two sets are different. So the two sets we are testing are different. So the smaller the p-value, the more confidence you have in saying that these two groups have different temperatures. So you don't really have to worry about, alternative hypothesis, the null hypothesis, and all that. It's so all that you have to remember is the p-value has to be very small, below 0.05, for you to be able to say with confidence that both of these groups are different. So by different, what do I mean? It means that the average or average temperature in these two groups, active and inactive groups, the average temperature, the means of these samples are different. That's what I wanted to say. So this is the way you calculate a t-test. What you're giving is you're saying the temperature, divide it based on the active groups. So that's like 2 and 0 and 1, and you give it the data set. So as I told you before, you have the t statistic, you have the degrees of freedom, you have the p-value. So this is for now, just worry about just this. It says the p-value is much less than e to the minus 16, which is 0.00016 zeros and 2. So which is much smaller, much very smaller compared to 0.05. So we believe that these two groups means are very different. But if you look at the actual numbers, right, you wouldn't be able to make out from these numbers. You would think, the mean of group 0, which is the inactive group, is 37.09, and the active group has temperature of 37.9, which is just 0.9 difference between these two groups. So it depends on the number of data points you have and what samples, consistent story that the samples are saying. That's why you would need these tests to show the significance. So we have a question. Dr. Venkat is asking to apply the t-test. It's important to check Shapiro test. If the data is not normal, we can still use Wilcox test. Correct. Yes. So that's what I meant to say. You always have to check for normality of data, which is through the Shapiro test. So Shapiro.test, use that test and see. If the p-value is bigger than 0.05, you can very well use the t-test. If it is not, you can always use the Wilcox test. Correct. Okay, so Wilcox test also follows the similar syntax. You have the temperature on the left-hand side, which is the Y, and active on the right-hand side, and you give it the data, and it runs the test. So you will have all this information printed out. So if you want to extract basically the p-value from this, you assign this to a variable, and then from that variable you can call it by $p.value. That's what I think. I have that in the next few slides. Yeah, so that's what I just have it here. So use the Wilcox test when you can't demonstrate that your data is normalized, and so basically what you're saying is you're looking for a location shift between the center of these both samples. Yes, that's what we are looking for, because we wanted to say that the means of these two groups are different. So one-sided test is a test that is used to see which one is higher or which one is lower. So because until now we just saw that whatever groups, the two groups that we are testing, we are just demonstrating with t-test and Wilcox test that if they are different, you're just saying they are different, but you are not able to say which one is statistically higher or lower. Of course, you can look at the means and say that you can look at the means and say that okay, group one is higher compared to group two. But there are one-sided tests. The previous ones are all two-sided tests. So the groups are always one-sided tests where you want to what you want to do is you want to check if your data above the mean or below the mean is uh, is is different in the two groups that you're testing. So this is again one-sided test is a very biased test. It also loses some power when you're checking for the whole data. So again, this is maybe it will be used with advanced statisticians trying to do and test for one particular thing, but we don't really use the one-sided tests in our daily work. So the next thing that you will frequently encounter is paired data. So what is paired data? Paired data is something that, say for example, you have some subjects taking treatments. So the before treatment values and after treatment values for the same patient is going to be paired. So usually whenever you use this paired data, you get an increase in power depending on how big your data size is. So say if your data size is greater than 30, something like that, if your data size is greater than 30, then using a paired test will improve your statistics because you're linking. Now you're saying these two groups, the two groups that you're testing, now you're saying that these are just not random circles, but they are linked together. I just wanted to see if I can show you. So you remember this. So the two tests that we are testing. So basically, in the t-test and Wilcox test, if you are not using paired data, then your points are like this. You're testing the difference between these two. But if you're using paired equals true, then you're linking each of these points. Say this is linked to, you know, so each of these points are linked, and then you're testing the statistical significance of the mean, which may be much more powerful depending on the number of samples you have. Usually whenever we have data for subjects and treatment before and after studies, we usually used paired equals true. So in your t-test, you have an option in your t-test and Wilcox test. You have an option which you have an option in your, let me show you in the help, as one of the parameter to be able to set paired equals true. So here this is the t-test and you have a parameter called paired. So usually paired by default is false, but if you have a paired sample set before and after treatment samples, you have to set paired equals true, and that will improve your statistical significance. You can still do the default paired equals false. So usually I see that whenever I have a smaller sample set, maybe like just a handful of samples, like 5 subjects or something, and say for the post time point I have only 3 or 2 and some of those are missing, then essentially by setting paired equals true, I'm losing the power. If I set paired equals true, in that case I use a paired equals false even though I have a paired data set. All right, so yes, So that's what I'm saying. In the t-test, you have paired equals true. So you have a paired t-test, and then you have values. So basically what it says is the differences in means is what you're looking for in the two groups that you're testing. So this is another data set that I used, and here I say what the data set is. So right after the class, please go through this. It's a data set called sleep, and it basically gives, again, this is also an inbuilt data set in your R, and what it has is excuse me, what it has is the number of hours of sleep after a medication, and it gives the different subjects and what variation the subjects have. So depending on that, for that, since it's a paired data set, the Beavers is not paired, it's a continuous time series data, and so but this sleep is a paired data set. So you can explore with that data set. You can use the same, try to do the same Shapiro test, check for normality, and use this. I already did that, and that's why for a paired data set, you kind of do this paired equals true. So you can check the Shapiro normality and then do the t-test with paired equals true. Okay, so let me complete this last part of it before. I was thinking I wouldn't have time for the models. So let me look at this last part, which is when you have data sets with counts and proportions. I know with one of the previous sessions we had looked at proportions, but let's look at one such example over here. What we are doing here is we are dealing with a data set with survival rates for automobile accidents based on whether the people had their seat belts on or off. So we have just four numbers here, 1781, there's four numbers, putting it into two columns. We are creating this matrix. We are creating this matrix and saying, oh, that's a typo. So it's like no seat belt and seat belt as the row names, and how many survived and how many died. So what we want here in this case is we want to see with people having no seat belt, how many survived and how many died. So what is the dead people proportions combined with all the people who were wearing no seat belt, and what is the proportion of the number of people who have died who were wearing seat belt. So this is so in order to check um, the proportions and their differences. So in this group, so in the previous Beavers set, right, we were looking at temperature for the two groups based on activity. And this is categorical data. So this is whether they have survived or died depending on whether they were wearing a seatbelt or not. So this is categorical data. So we cannot use a t-test in order to see the differences or the proportions in between these groups. So we use something called a chi-square test. So we could use, so in a chi-square test, chi-square test is something that you use to test significance of the differences between two groups depending on whether they are categorical data. So for a t-test is used for continuous data, but a categorical data you use a chi-square test. So chi-square test, with the chi-square test you can see the significance of or the proportions difference between the two. For just a proportional difference, you use this method called prop.test, and then you pass it the matrix that we just created, the survivors matrix, and then you see the results of those of this prop.test. Again, it's a chi-square test. It's a so that x squared is the measures that you see for um, for uh, for a chi-square measure. It's an x squared. It's a chi-square measure. Again, you don't have to worry about this. But look at the p-value. The p-value is very strong depending on the probability and the proportions. Look at the proportions of 1 and 2, which is for the two groups. So right now we are looking at two groups, the survived and died depending on seatbelt and no seatbelt. So the two groups, the proportions is like 96.8% in one, and 92.9% in one. To check the differences between these two groups, this is what we did. And just to check for a chi-square test between the two, it's going to give us this is not proportions. This is just a chi-square test, and to not check for proportions, you do this prop dot test. So chi-square test, you have the chi-sq dot test. You can do the two. This is not a chi-square test. Just to demonstrate the chi-square test, I have this data set where we are not just looking at two columns, but we have more than two columns. So whenever you have more than two columns worth of categorical data, what you have to do is you have to reduce your matrix into just the two that you're testing for. So here is one other data set that I have used. So you can experiment with this after the class. It's a hair eye color data set, and it has more than two, which is almost three categories, which is the hair color, the eye color, and male or female. And depending on that, what we do is we reduce that in order to use a chi-square test, we reduce that using margin dot table just to one or two of these columns. So I'm using 1 and 2, which is just the hair and eye color, irrespective of whether they are male or female. So just depending on that, we create this matrix where we are saying hair color, black, brown, red, blonde, eye color, brown, blue, hazel, and green. Depending on that, for people having black hair, brown eyes, and the matrix will be a tally of the data set. And then you do a chi-square test, and it's going to distinguish the columns of these, and it says that each of these categories is very significantly different from one another. So modeling I'll cover in the next class. Until now, just I think today we have just covered the statistical testing of these, just to see the differences, and also the lattice library, using how to do the histograms and check the normality of data. So any questions so far? We'll stop here. Oh. Okay. I was thinking I lost everyone. Anyway. Yes. So correct. Yes. So this is for the text mining, right? So for the text mining, yes. For the text mining, sorry, I didn't send you those files, but yes, I will send you right after class today. So let me